I'm happy to announce today a talk by Carlos Meriles. Carlos was born and raised in Cordoba, Argentina. He obtained his PhD in physics at FAMAP, the Mathematics, Physics, and Astronomy Division of the Universidad Nacional de Cordoba, under the supervision of Professor Brunetti. His doctoral studies focused on the use of nuclear quadrupole resonance to probe structural and dynamical disorder in organic crystals. After graduating in 2000, Carlos joined the group of Professor Alexander Pines at the University of California, Berkeley, to work on nuclear magnetic resonance, his present field of research. In 2004, Carlos joined the Department of Physics at City College, where he now teaches as a professor. Carlos, we are all grateful for you to give a talk today, and please, the stage is yours.
All right. Thank you, Olga, and thanks to all the Adamas team for this opportunity. And before I get started, let me apologize to the audience. The conditions today are not going to be optimal. There's been a number of recent developments that forced me to deliver this talk from far away from where I was supposed to be. And that's actually the reason why I have to wear this mask. So if you happen to not hear me well, or things become unclear, please feel free to interrupt at any time, and I'll be happy to repeat or clarify as needed. Well, as you can tell from the title in the presentation, this talk is going to be centered on recent results that we had in the laboratory on the optical activation and observation of transport between individual defects in diamond. And to give you a little bit of motivation and context, I think I will first start by saying that it all began a couple of years ago. In my group, we started thinking about a pretty simple and, if you will, crude idea. So we knew at that point in time, we knew, of course, that optical excitation could spin polarize the NV centers. And we also knew that optical manipulation could change the charge state of the NV. And so the idea that that we started discussing was, isn't it possible to spin polarize and inject a spin polarized electron into the conduction band of diamond? And it so happens that diamond is a nearly ideal platform for spintronics applications. It has a centrosymmetric structure, very low spin-orbit coupling, very low content of nuclear spins. And yet there's essentially no studies of spin injection in diamond, precisely because the injection through standard means is rather impossible. And well, it so happened too that at that point in time, I started having some discussions with my friend, Marcus Doherty, in Canberra, Australia. And we started to think of the carrier in perhaps more general, more ambitious ways as a bus to transport coherently information between, let's say, qubits in diamond or some other wide bandgap semiconductor, separated by a few microns. And so over the last few years, what we've been doing in the laboratory is to sort of gain the know-how and put together the physical infrastructure that is needed for this type of experiments. Apologies because of the background.
Oh, it's no worries, it's just background. We can hear you very well.
Okay. Now, before I move forward, I want to emphasize that that in no way my group is the only one working along these lines. As a matter of fact, there's a number of other groups working on related topics and more broadly applications of charge manipulation to different forms of sensing, for example. And just as an illustration, I decided to highlight this particular paper by the Gillesco and Nesladek groups. In this case, what they do is they use a very strong green beam to illuminate an individual NV that happens to be inside a diamond where they patterned some electrodes, interdigitated electrodes here. And the idea is that with this strong beam, you can, as I'm going to explain in a few minutes, you can actually change the charge state of the NV and make it cycle between the negatively charged and the neutral states. And every time a charge state change takes place, you are inputting an electron or a hole into the conduction of valence bands. And so in this experiment, what they do is they detect the current that is produced by these photogenerated carriers. And so here on the upper right, what you see is an individual NV, the confocal image of that individual NV obtained by standard means. What you see down here is the electrically detected image of that same NV as they displace these excitation beam from one point to the other. Now, this is, as I said, just one illustration. This is an active area of research, and down here I've listed some of other groups that are also working on these or related directions, and this, of course, is just a reduced list. I'm sure there's many others. Now, I know the audience in this presentation is rather broad, although I'm pretty sure you all know about the NV Center. So I'm not going to introduce so much the NV Center itself. Rather, I'm going to refresh some of the aspects that have to do with the charge dynamics of the NV. And before getting into that, let me simply start by saying that NV centers and in general defects in semiconductors take different charge states. Very commonly, they take different charge states, and similar as when you move in the periodic table from one atom to the other one, and you add or subtract an electron. The same applies to color centers. When they change the content of electrons, their properties, optical and spin in particular, they change quite dramatically. And the relevant example for this presentation is, of course, the NV center. In the negatively charged state, the NV minus has a ground and an excited state that are separated by 1.9 EVs, the equivalent of 637 nanometers. However, if you go to the neutral charge state, what you find is two states that are separated by 2.2 EVs, or the equivalent of 575 nanometers. And that essentially allows you to distinguish, for example, just using fluorescence, one charge state from the other. In particular, in all the experiments, we're going to set our microscope so that the neutral state appears as dark and the bright state is the negatively charged. Now, there's different ways that you can imagine using for controlling that charge state. And here I'm just going to give you an example. So let's imagine that we start from the negatively charged state and we use red illumination. And in particular, let's imagine that the beam is pretty strong. And so it's sufficiently strong so that when we first excite the NV center from its ground to the first excited state, a photon arrives before the system had time to relax. And so when that happens, then there's an injection of an electron into the conduction band, and the system as a whole transitions to the neutral state. Now, you realize that once in the neutral state, red photons don't have the energy to excite NV0 any longer. And so the transformation is, in this sense, one directional, in the sense that it goes from NV minus to NV0, but it cannot go back. Now, of course, we can recover the negatively charged state. And for example, we could use a green illumination for doing that. And so in that case, one first photon would excite the neutral NV into the first excited state. And then a second photon would excite an electron from the valence band. And so we transition to a negatively charged state. And we also are left with a diffusing hole. So now notice that green excitation also has the energy for exciting and eventually ionizing NV minus. And so then green illumination creates a back and forth between NV minus and NV0. Now, it so happens that the probability for producing NV minus is under green excitation a little bit higher than the opposite. And so throughout the presentation, we're going to see experiments where essentially we say we initialize into NV minus. That should be understood as a probabilistic initialization of the charge state of the NV. So before these experiments that I'm going to be presenting today, we've done a lot of work along these lines. And here I simply wanted to give you some taste. These are images, confocal images, where we use, for example, a strong green beam to initialize the left side of this field of view into the negatively charged state, a red beam to initialize into the dark neutral charge state. And then we park a strong beam of different colors here right at the interface. And then we look we use another weak red beam to read out what the distribution of charge looks like. And what we find are different patterns that contain a lot of information in terms of how carriers, electrons, and holes diffuse and get generated and ultimately get trapped. And so these papers over here somehow reflect the gradually improved understanding that we've gained over time about these dynamics. Now, one thing that perhaps you already noticed is that the ability to show these images already implies that these charge patterns that you've created stay for long. And so, of course, then with that in mind, you could imagine patterning these charge states in a way so that you can store classical information. And so this is an example where we first prepare the ensemble of NVs into the negatively charged state. And then we use a red beam to go point by point and store some arbitrary pattern that later on we can erase and rewrite. And we can do this at will. And of course, this can also be done in 3 dimensions and has a resolution of, it's very much limited by diffraction. Now, most recently, we've repeated these same type of experiments, but in the presence of potential or of electric fields created by electrodes in the vicinity. And we see these patterns evolving um, depending on um, depending on the voltage that we apply. And in this process, we can extract information about the space charge potentials that are created through the ionization and diffusion of these carriers. Now, today, we're going to move to something different, and that is different because rather than looking at ensembles, we're going to be looking at very small ensembles, ideally individual NV centers. And to make this happen, we teamed up with people at Sandia National Laboratory and used a very strong ion implanter to create these islands, some of which I show over here. Controlling the fluence in that implantation process, you can of course control how many NVs you create. And on occasions, we find islands that contain just a few NVs as shown over here. Sometimes we manage to identify individual NVs that happen to be separated by a few microns. And we can use them now to start trying to see how the transport of carriers, the photo generation and transport of carriers between these individual NVs takes place. Now that these are individual NVs and not some a bunch of NVs all clustered together, you can see here when we take the autocorrelation functions, you see dips that go below 0.5 and indicate presence of an individual defect. If you take, for example, a time trace like this one, you see blinking that is characteristic of a defect changing its charge state from a dark or neutral state to a bright or negatively charged state. So with this sort of system now, you can imagine the following type of experiment. So let's imagine we use two beams, and we first use a green beam to initialize both NV centers into the negatively charged state. So this would correspond to this initialization stage over here. And by the way, I'm going to be referring to these NVA and NVB as the source and the target, meaning that this is the one where carriers are going to be generated. This is the one that ultimately is going to reflect the capture of one such carrier. So the idea is that after we've initialized these two into NV minus, then we park the green beam into, say, NVA, and we leave it there for a time. That typically is on the order of a couple hundred milliseconds. And then we use a orange beam to go and see what the charge state is. Now, this is the type of results that we observe. So this is what we first get if there's no parking at 0 milliseconds, the evolution time or the park time. This is what happens as the park time increases. And what you see is essentially that the target NV becomes less and less bright. And this we interpret as the result of the capture of a hole that was generated from NVA. And that rendered the target NV initially in minus state, now a neutral NV. This plot over here shows perhaps a more quantitative evolution for different laser powers. And perhaps the takeaway message when looking at this image is not so much the main plot itself, rather this insert that I'm showing here in the upper corner. I'm not sure, sorry, I'm not sure if you can see it because I have some interference here, but okay, so there you go. So this is what I wanted to highlight. When we plot the these bleaching rates as a function of the laser power during the park, what we see is a quadratic behavior. And this quadratic behavior is already consistent with the fact that there's a two-photon process associated with the ionization and recombination at the NV, at the source NV. And so this is already indicating that the source NV is actually the only source, and there's nothing else over there that is also creating some background defects. Oops, something happened. Yes. All right. Now, as experimentalists, I think we all know that it's very difficult to guarantee this that I was just saying, that the NV is the only one creating defects. And so we went to great lengths to make sure that that was actually the case. And one strategy that we used for that was to make use of the spin states of the NV and a protocol that is called spin to charge conversion. Now, I won't get into the details as to how spin to charge conversion works, but I will just give you the main idea, which is the fact that the NV has in a ground state these essentially doublets between the 0 and ±1. If the NV is in 0, chances are that once excited, the state of the NV is going to be this one, and there's going to be no cross relaxation with these manifold of singlet states. And so if that is the case, then there's a pretty high chance that this second photon arrives while in the excited state and then ejects the electron into the conduction band. Whereas in the opposite case, if it was, say, ±1, then there's a larger chance of this intersystem crossing. And because the shelving time in the singlet manifold is higher, the rate of generating electrons in this case reduces. Okay, so essentially what we have is a way to ionize the NV minus conditional on the spin state it is in.
Yeah, thanks for your help. I'm going to grab a couple more of those issues.
Okay.
Oh, thank you. Thank you.
All right. So this is actually the protocol that we're using. It's a bit more complicated than what we had before, but conceptually it's relatively simple. As before, what we do is we initialize both the source and the target NVs into the negatively charged state. And we finally will probe in the same way. But instead of just parking a beam for a long time, what we're going to do is we first spin initialize the source NV into, say, ms equals 0. Then we will apply or not microwave at some frequency. And then we will apply a pulse. You can think of it as a red pulse that is going to ionize the NV. And hopefully that ionization is going to be conditional on the spin state. And we then repeat that multiple times, and we look at the result with an orange scan. So these that I'm showing here on the upper right are two images of the source, of the target NV. This is before we apply this sequence. This is essentially the reference fluorescence that we start with. And this is what happens after a couple repetitions. There's no microwave applied in this case. And what we see is just some bleaching coming from the holes that are being generated in this process. Now we turn on the microwave. And so let's imagine first we set the microwave away from the resonance frequency of the ground state. It's this case here on the right. And what we see is that the fluorescence that we obtain is pretty much the same as what we had in the absence of microwave. And that is simply because off resonance frequency or microwave doesn't have any impact on the NV charge state. On the other hand, if we set the frequency to be on resonance with that transition in the ground state, what happens now is that the population of ms plus minus 1 grows. And so as a result, we eject less carriers into the conduction band. And so we have less chance of a capture. So then the target NV remains brighter than otherwise. And we can repeat that same protocol as a function of frequency. And so what we get down here is the equivalent of an ancilla aided magnetic resonance spectrum of the source NV, which agrees reasonably well with the traditional ODMR or optically detected magnetic resonance spectrum of that same NV. Now, a comment that I want to make before moving forward is that the contrast that we get over here tells us that essentially just this one NV, the one that is serving as the source for the ionization or for the charge state change of the target NV. So the picture that emerges is one where essentially we have a source NV that is sort of generating carriers radially. And because we know the distance between the two, the source and the target, and because we also know the rate at which these carriers are being generated, then we can calculate what is the probability, the capture probability, and from it calculate what is the capture cross section, the whole capture cross section for an NV minus. Now, the number that we get is actually quite large, and I'm going to get back to that in a couple of minutes. It's about 50 by 50 nanometers squared, which is a number that is surprisingly large if you go to the literature and compare with what people have measured in ensembles. But let me get back to that in a second. And before, let me address the fact that we have this image of carriers emitting radially. And this is also something that we've confirmed by taking different pairs of NV centers. Different pairs of NV centers separated by different distances. Say, for example, this one has 5 microns. In this case, the two are like almost 9 microns away. And in each case, we repeat the same type of experiments we had before, and we measure what the bleaching rate of the target NV is, and we plot that as a function of the distance. And what we get is a dependence that goes with the inverse of the distance squared, which is what we'd anticipate for a sort of isotropic emission of the carrier from the source end. Now, the physical picture behind the observation of these large capture cross sections can be somewhat rationalized if we start, if we realize that as a whole approaches the negatively charged NV, there's a strong Coulombic interaction that takes place. And so essentially what happens is now we're going to be dealing with hydrogenic states. And these hydrogenic states, because of the long range of the Coulomb interaction, is going to essentially create is going to lead to these large capture cross sections that we see here. I don't have the time to go into that into these in detail, but we've done DFT calculations that partly, and I say partly because DFT doesn't have the capability to really go to long distances, but at least the results that we get are consistent with this understanding of the formation of what we call a bound exciton, an idea that, by the way, was introduced first by Mel Lax in the 1960s, and that I have to say most recently has been invoked in some other related articles. Here I'm highlighting two. In this particular case, they sort of invoke this idea to explain observations of carrier recombination at single NVs in a PIN junction. Most recently, the group of Natalie de Leon reported the observation of bound exciton states in silicon vacancies. So these are ideas that have been around, and our observations are consistent with these ideas. Now, I'm going to use the last minutes that I have left to tell you about ongoing research activities that are related to these observations. Two in particular. One is more involved than the other one. I'm going to start with a less complete picture because I think it's just going to be clearer. In this particular case, we return to the geometry that we've been discussing so far, and we keep everything unchanged except that we're going to be using electrodes to control the carriers that we generate, induce a bias in the propagation. So in this plot over here, what we see is the bleaching rate for a given fixed laser power during the park, but different voltages that are applied. Now, in this case, we apply positive voltages, meaning that carriers that are generated here by the left NV, the source NV, tend to propagate actually to the left, that is against, not towards the target NV. And so, as expected, what we find is that the bleaching rate decreases to finally disappear. So we preserve the charge state by simply of the target simply by redirecting the carriers, holes in this case, in the opposite direction. Now, something less intuitive is what happens when we change the sign of that potential. In this case, we apply negative potentials, and in that case, we bias the carriers towards, not against, towards the target NV. And what we see is that as we increase the voltage, the bleaching rate also decreases as well. And all these has been captured in this plot over here, where we show the bleaching rate as a function of the applied voltage. And we find that there's a maximum precisely when we don't have any voltage applied. Now, I don't want, because I don't think this is fully ready yet for prime time, I won't get into a detailed explanation. All I will say is that for now, we have Monte Carlo calculations that sort of confirm almost quantitatively this picture. And briefly, there seems to be an interplay between the enhanced density, carrier density that we generate with negative potentials, and the acceleration that we induce in these carriers that somehow combine to yield a lower capture probability. But this is something that I'm going to postpone for later. Now, another aspect that I think is interesting, and where we've done some more work is this one. I think this one is interesting because it shows, I'd say, the first application of something that may seem to many too fundamental. So in this particular case, we are repeating the same type of experiments as before, except that now we're going to move the position of the park beam around the source NV, and we're going to be monitoring the target NV. Notice we're changing slightly the language here because we're using this to see what's happening here at the source. We're going to be referring to the target as the probe NV. And so this one is just a standard confocal image of that probe NV. This one is the what we call the carrier to photon image, or CPC image, of that same source NV, as measured by looking at the probe NV charge. So we see essentially, and notice that there's an inversion in terms of the colors. Here, when we have a source of carriers, what we find is a dip rather than a peak like over here, right? And that's important because now things are going to become a little bit more complicated. So you want to actually keep that in mind. A comment that I want to make also is that if we were to change, here I'm indicating, down here we're indicating what color we're using for the park, or in this case, what color we're using for the readout during the confocal. And so if instead of using a green park, we transition to a red park, what we see is that essentially this image disappears, and that is consistent with the fact that the NV gets ionized once and there's nothing else happening. So the charge state of the probe NV remains unchanged. And this is actually confirmed directly here in the confocal image. We don't see the source NV simply because we ionize it almost immediately and we don't have time to collect photons. Now, with this in mind, what we can do is, of course, image not just individual NVs, we can image, say, collections of NVs, and this is an example. So in this case, we have the probe NV located over here, and we have these islands of neighboring NVs. The CPC image that emerges is this one that I'm encircling here. You can see, if I know the resolution is less good as, or worse as compared to this one, but still you can see that there's a one-to-one correspondence between the source NVs that are acting here and what we can see in the CPC image. Now, so far, we've been looking at, say, other NVs, but let's now make things a little bit more interesting. Let's try to go and see defects that are not necessarily the NVs. And one idea that we had was to look at silicon vacancies and see if silicon vacancies could also charge cycle. So what I'm showing up here is a region that we implanted with silicon to produce silicon vacancies. And that these are silicon, negatively charged silicon vacancies is shown in these spectra, or in this spectrum. There's this peak that is characteristic of negatively charged silicon vacancies. Now, if and this image can be selectively made selective to silicon vacancies using red excitation. Now, if we were to use green excitation, and here we're looking at confocal images, we already find something interesting, and that's the fact that there's NVs over a region that is much larger than the region that we implanted with silicon. The way we interpret this observation is that the implantation of silicon produces lots of vacancies, which subsequently diffuse during the annealing for produce that is typical for producing the silicon vacancies or NV centers. And so the result is that then these vacancies diffuse and pair up with some existing nitrogen that that leads ultimately to the formation of a negatively charged NV. So this is already something that caught our attention. Now let's go back to these indirect imaging. And so let's first focus on this particular region over here. Remember, we were trying to see if the probe NV that is located here is not visible because we're illuminating with red. Here you can see a faint image of the probe NV when we illuminate with green. Okay, so this is our probe, this is what we scan, and this is the CPC image that comes out. And what we find is that there are some regions over here that seem to be emitting charges. And so that essentially translates into a bleaching of the probe NV. Now, if we were to compare this image with now the image of silicon vacancies in this region, what we see is that there's essentially no correspondence. As a matter of fact, you see that there's emission from places where there's no silicon vacancies. Remember that red excitation precludes NVs from even producing a meaningful number of carriers. But if we were to also look at the confocal image via green excitation of that same region, we also find that there's no correspondence between, say, what we see here in the CPC image and what we have here for the NVs. Now, perhaps we can make the case clearer if we actually move our spot from this point where there's lots of silicon vacancies to this other spot where there's no silicon vacancy. There's essentially no fluorescence. And what we see here is, again, the presence of charge emitters that lead to a bleaching of the probe NV. The confocal image of that same region yields no fluorescence virtually because, as I said, there's no silicon vacancies. If we were to look at the NV centers, once again, we see that there's no correspondence. We have emission from regions that do associate with NV centers. And once again, I insist, NV centers via red excitation cannot yield any charges, as we've already seen. So, of course, we are left with the question of what those defects are. I mean, on the bright side, there's the fact that we can now see charge emitters that are dark, and that essentially they do not fluoresce, at least in the range that we've looked at. But we are at a point where we don't know exactly what those are. We have some ideas, some possibilities that I think are worth exploring, but there's nothing concrete at this point. Now, on the other hand, there's you can think of this sort of imaging as a sort of alternative to PLE or photoluminescence excitation. And in the same way, you can imagine doing a sort of spectroscopy, and through that spectroscopy, gain some clues as to what that defect, that source charge emitter happens to be. Well, we haven't done this yet, but we've done some steps in that direction, and these are results. Here, what we do is we plot the bleaching rate for different red excitation powers, and what we see is this change. If we were to plot the rate now as a function of the power that we use, what we find is this linear regime. So remember, in the case of the NV, we saw a quadratic dependence. In this case, this is telling us that the process is one photon, not two photons. And then somehow mirroring what happened with the NVs, which was active under green excitation and not under red, In this case, if we were to use green excitation, we see that there's no bleaching. So essentially the bleaching rate of the probe NV remains at virtually 0. So whatever model essentially we come up for what that charge defect or that charge emitter is, has to now fit these spectroscopic observations that of course can be completed with additional measurements at different wavelengths. So, well, I think I'm going to conclude here. I can summarize this presentation by saying that well, we've been able to observe, to generate and observe the transport of carriers between individual defects, small groups in general, and down to the level of individual defects. We use spin to charge conversion to filter out any potential contribution from background defects that are not taken care of. And we found that, well, in the examples that we looked at, the NV was the sole source of these carriers. We also looked at dependence with distances to find out that to conclude essentially that the emission of carriers from the source defect is isotropic, at least in the unbiased case. We also used all these that we learned to highlight or to expose charge emitters that, well, are not fluorescent and therefore are invisible for practical purposes. And as a concluding point, I would say that we are now left with pretty, at least in my view, a pretty interesting prospect, because that I think, you know, points in different directions. There's the fact that the very formation of these large orbits that translate into these large capture cross sections points to the existence of Rydberg states in the NV. And whether those Rydberg states can be generated and controlled is, to me, something that seems quite intriguing, and a direction that we will certainly explore in the future. And there's, of course, all that's related to the spin degrees of freedom, either for the injected carriers or alternatively the spin state of the source, of the target NV, that can be also manipulated, and where we think ultimately we're also going to see an impact in the capture probability, allowing us perhaps to identify the very injection of spin polarization or spin polarized carriers that we first that motivated somehow this presentation. So with that, I'm just going to acknowledge my group. This is a rather old photo, but I have people who have already left, and I wanted to make sure that they are properly acknowledged. Hattie among them, and Aisha, as well as Damon, but most importantly, Arthur, who's been leading all these efforts. And I, of course, have to also thank my collaborators at Sandia, Marcus Doherty, and I'm forgetting, and I'm embarrassed by that, but I'm forgetting about Johannes Flick, who has been helping us, who's been central to all the DFT calculations that we did on this topic. And with that, I want to just thank the funding agencies and you all for your patience. Again, these have not been the best conditions for me. I apologize for that. Thank you.
Carlos, on behalf of everybody, our applauses. It was brilliant presentation and amazing work. Thank you very much. And thank you for being so persistent to find a spot in emergency facility and deliver this brilliant talk. Thank you very much. So I will start with questions. So Jim Butler asked and commented, very elegant work. Can you comment on the role of other impurities on your observations, namely NS and boron? Probably these are your dark impurities that you're talking at the end of your talk, but please elaborate more specifically on these donors acceptor type impurities.
Yes, so that's actually a good point. I have to confess that we haven't looked at the boron content. All I can say is that the sample that we used is of the highest quality. It's electronic grade, and we've been told by the manufacturer that the concentration is something in the order of background concentration of nitrogen is something in the order of 10 to the 14 per centimeter cube or less. As a matter of fact, when you, if the notion that I was trying to lay out when we saw that formation of NV centers around the spot of silicon implantation, if we were now to go and directly count how many NVs form and assume that all these NVs form because there was already a nitrogen there, we obtain a concentration that is very much in agreement with what the manufacturer told us. So that seems to be consistent, and typically, and here I may be wrong because I'm not that expert in diamond growth, but my understanding is that nitrogen is by far the more common impurity. So if nitrogen is at that level, then I would anticipate that boron is actually way below that, unless otherwise incorporated. And even though that's typical, especially if you want to create SiB zeros, for example, well, this is certainly not the case. We've kept the sample pristine, except for the implantation of nitrogen.
Thank you. Next question is from Stefan Diggs. Very nice talk. I have a question concerning the SCC protocol. Which kind of laser do you use to ionize the negative NV center? I've seen people showing SCC protocols with an resonant shelving pulse at 637 nanometer, but others use protocols with 589, 594 nanometer laser. Is there an advantage to use one over the other?
Yeah, so here I have to say that yes, all these that that is being said is correct, and probably you know, this person knows that the conditions for a spin to charge, for an optimal spin to charge protocol, are still very much a sort of you know, optimization process. There's the process is known but not perfectly understood, and so, for example, this combination of green and red is something that was introduced rather empirically, with the idea that, for example, this weak green beam would help the excitation of the NV to the first excited state, and then the red would actually create the ionization. That was the rationale for it, and it turns out that it works reasonably okay, and we get better contrast doing it this way rather than going, you know, in some other possible way. But that is the only reason. It's just that experimentally we find that these conditions seem to be optimal, and this is what allowed us to see this contrast that otherwise is pretty difficult to pick up.
Thank you. I also have a question. How robust is this charge cycling process? So, can you repeat it over time and it will perform similar, or it can degrade over time due to some reasons?
We haven't seen any change, but here I have to emphasize something that perhaps I didn't highlight enough, which is that when we created, let me go back to this slide, when we created these islands, we made sure that these islands were sufficiently deep inside the diamond. So you see here in the cartoon, it's about 10 microns, 10 to 12 roughly is what we find when we go and look with the confocal microscope. And the reason we wanted to do it this way was that we didn't want to deal with processes that alter the charge dynamics close to the surface. And in prior work, we've seen that changes in the photodynamics of NV centers can be quite dramatic. You can even see one photon processes and linear growth with power. You can see all sort of things. And so this would only complicate the overall picture. So, so by going sufficiently deep, and this was possible at Sandia because they have these high energy implanters that we took advantage of, then we put those concerns to rest, at least for now. Of course, if now we were to go, say, closer to the surface, and there's a second round of samples that are being engineered with these conditions because we want to couple to structures that we create on the surface and move these a little bit higher in terms of sophistication. But it could well be that this all fails because the surface termination of diamond is not the right one. And we've already seen, not in these sample that I was talking about, but in some other samples that were given to us for test, we've seen that you can actually create non-reversible changes in the charge state of the NV when you are very close to the surface. So that's the only caveat. What causes that, and whether that can be avoided? Personally, I think that is the case. But exactly what causes it and how to circumvent the problem is unclear yet.
Thank you. Please ask your questions without typing. It's easier just to unmute your microphones and ask questions. It seems everything, the connection works very well.
Carlos, just a comment. I think you've developed some really powerful tools here, but I would be interested in seeing them eventually get applied to diamonds that are not as pure as you're working on now, such as natural diamonds or lab-grown diamonds where we know we have phosphorescent processes that are involving charge transfer. It may be very interesting to apply your techniques to those kinds of stones.
Yes, I fully agree. And that is somehow a line that branched out from this work. And so now, as we speak, actually, we're completing measurements. Once again, we're dealing with type 1B samples for now, because there's the caveat that if the impurity concentration is too high, then these metastable charge states that last pretty much forever in the dark in these type 1B samples may not be so long-lived in samples that have a very high impurity content. So that's something to keep in mind. We've seen that happening with samples where the NV concentration is really high, on the order of, say, tens of ppms, and nitrogen is on the order of hundreds of ppms. So we know that we can ionize, but we can actually see on the, say, I'd say few milliseconds, tens of milliseconds, I'd say, time scale, that the charge states that we create sort of bleach out. So there's that point to keep in mind. But if the concentration of impurities is sufficiently low and these type of images become possible, then there's a number of opportunities, and one that's actually we were discussing yesterday in the laboratory was the fact that we can now tell via the help of electrodes to bias the carriers in one direction. We could actually tell what type of charge state the silicon vacancy is taking when exposed to carriers. So initially we were thinking it would be, we know for sure these are non-fluorescent states. We were very much hopeful they would be neutral silicon vacancies. We've now seen via these electrodes that's actually not the case. We have to believe it's we believe it's the doubly negatively charged silicon. But that's just, you know, an application that comes out in ensemble samples.
Mhm.
Well, I'll jump in with I guess one quick question, kind of a higher level, because I think these characterizations that you're doing are I mean, they are, I think, as Jim said, very elegant. But you opened saying that, you know, this was in the vein of almost a communication bus, and that implies that you're actually thinking about an application or some sort of information transfer. And I'm wondering if you foresee something like that in the future, and what if you have any applications in mind for actually communicating between the different centers.
Yeah, so that I would say is the silver line of these work. And I don't want to make statements that later on I'm going to have to withdraw when we see that is not possible. At least on paper, and this was mostly the work of Marcus that I highlighted early on, things are possible. There's one important parameter that here I haven't actually exploited, and that we are now trying to make part of these observations, which is, of course, the temperature. I mean, all these that I described took place at room temperature. We have reasons to believe, based in part on these Monte Carlo simulations that we've been running, that things are going to improve for the better as we lower the temperatures without necessarily going to ultra low temperatures. We think that something in the order of liquid nitrogen would already make quite a positive impact. This is in terms of propagation distances and scattering processes. So we think that there's a bunch of things that are going to happen as we lower the temperature. First off, I have to say that the spin state of the NV, even under near ambient or near ambient conditions, are predicted to be 10 times better than silicon already. So nobody, as far as I know, has been able to prove that. And so there's experiments, I think, that we can imagine where we first try to see if we can deterministically inject spin polarized carriers into diamond. That was, I think, the initial idea, and it's the simpler one. That in itself, I think, and this is, of course, not quantum in the sense that quantum, it's still classical spintronics, but I think it would be interesting to see that happening given these near ideal features that diamond has. Connected to that, there's of course the fundamental knowledge that comes from say looking at capture cross sections that can be made spin dependent, for example, by controlling the spin state of the target NV. If all that is put in place, and that's a big if, then you can start imagining processes where now you can encode information in these flying qubits that take the form of either holes or electrons, and imagine transporting these information coherently. That would be a dream for now. So I have to be clear on that.
Oh, that's really great forward-thinking perspective. Yeah, thank you.
Carlos, thank you very much. Please let us know if anybody would like still to ask a question. And it seems everybody is happy with the presentation and the previous answers. So Carlos, on behalf of everybody, again, thank you very much for your excellent presentation. And we wish you good luck in your research, and all your dreams that you outline will come true eventually.
All right. Thank you.
Okay.
Thank you, everybody.
Bye-bye, everybody.
Bye-bye.
Thank you for your attendance.